Okay, welcome back everyone. I hope you had time to enjoy some coffee and stretch your legs. Reminder that to please complete your survey at the end of the day. That way you can be entered for a prize in our draw. And our next presentation here in the water stream is Things We Can Do to Tackle Climate Change by Chris Howarth. So Chris is a registered professional engineer in BC with over 20 years experience in water and wastewater treatment. He graduated from the University of Plymouth in England with a degree in civil engineering. He has worked for both private and public sector organizations in Europe and in Canada. He is currently responsible for municipal business development in Western Canada. Please welcome Chris.
Thank you, Chris. And thank you, everybody, for choosing to listen to my presentation this afternoon. So I'm going to be talking about things we can do to tackle climate change. I should say that climate change can be a bit of a contentious issue. So I'm trying to avoid politics here. I'm trying to keep it factual. Really, this sort of the first part of the presentation is really big picture, what's going on with the climate. I think it's fair to say that most people now would accept that we've got an issue. The climate is changing very significantly, and it's a concern for a lot of folks. So trying to look at some of the sort of data around that and really where we stand. Is this an issue or not? How serious is this, I guess you could say. And then going on from there into what we can do about it. So what does this mean for the water industry? What are the sort of specific issues we're facing in the water industry? And what are the things we can do to tackle those issues? And what are people doing to tackle those issues? So I will just open up something here quickly. Bear with me. Thank you. So, okay. Population and carbon emissions. So what you're seeing here is global population. The green is the number of humans on the planet. On the left axis there, and then carbon emissions on the blue, on the right axis. So what this is showing is that there's a close correlation, right? And that kind of goes both ways. As there's more people, we're using more fossil fuels, and that's releasing more carbon into the atmosphere. But perhaps more importantly, the other way around, those fossil fuels have enabled the human population growth that we've seen over the last 100 so years. The oil and gas industry has been a great benefit for humanity. I don't want to underestimate this. We should all be very grateful for the prosperity that fossil fuels have brought to us. There's no way we could have 7 whatever billion people that we now have on this planet without having exploited fossil fuels. It's been incredible. The progress we've made over the last 100 years as a result of fossil fuels has been incredible. And like I say, we should all be grateful for it. I guess the question is, how long can that continue? Is it realistic to expect that the next 100 years could also be enabled by fossil fuels? Probably not, is the honest answer. And this is sort of part of the reason why global temperatures are increasing. It's pretty clear that there's a trend here. And this is comparing, so this is saying that in 2018, there was a 0.85 degrees Celsius increase over the average, and the average being measured between 1951 and 1980. Of course, by 1951, we'd already burnt plenty of oil and even more coal, so arguably, the real increase over what would be the natural temperature is probably around 1 degree, maybe a bit more than that. So temperature is increasing, and that's putting more energy into the climate system. The whole thing is getting more energized, and that's why we're seeing more extreme climate events. This is something that was put out by the BBC News just recently. Needs a bit of unpacking. So Biodiversity Index, what does that even mean? What they did is, this is a compilation of a bunch of data, a lot of different research activities going on around the world. They looked at in the order of 20,000 species of animals, so mammals, fish, reptiles, all sorts of different animals, and they looked at how much of those populations have declined since 1970. And what they found is that the decline was about 68%. So there is now 32% of the population of all of those 20,000 species that there was back in 1970, just over that short period of time. For me, that's a crisis, right? I mean, we can't impact the natural world that significantly, lose that many animals from nature, and have that not be a problem. I mean, we're part of the natural system. However we look at this, we're on a finite planet. And when you think back to that initial slide, there's a very thin layer that is the biosphere, that bit that life lives in between, the rock and the magma and the cold, hostile space is really quite thin. So there's not a whole lot of biosphere when you really look at it like that. So when we have such a great, huge population, and we're having such a prosperous form of life, then, we are causing quite a lot of impacts on that relatively small biosphere. And that's why we're seeing these kind of impacts. So some people are calling this situation, this loss of nature, the sixth mass extinction. To put that in perspective, the fifth mass extinction was when the asteroid hit the planet and killed dinosaurs 68 million years ago, or whatever it was. Huge loss of species. Also a huge problem, of course. Yeah. So you've probably guessed by now that I wasn't born in Canada. I was born in England. I've lived in Canada about 12 years now, and I'm a Canadian citizen. I'm very grateful to be a Canadian citizen. Thank you for having me. It's a great place to be.
I agree.
But I guess we could all be doing more. That's the point I'm trying to make here. I'm not trying to say Canada's terrible and the UK is amazing. That's, like I say, I don't want to get into politics here. I think it's safe to say that Canada is not meeting its targets. The targets it set for itself at a federal level to reduce emissions. And really, as I say, for me, this is a serious issue. We should be doing something about that, partly for the animals, but also, as you'll see in just a moment, for other reasons as well. And really, we owe it to our kids to do this. I've got 2 daughters, and they worry about this stuff for sure. I guess really the point here is that we are running out of time. I heard it put quite well that we're the first generation to really appreciate the situation we're in, that there is an issue here that we really need to address. But we're the last generation who can do anything about it. If we don't deal with this soon, this is all going to get away from us. As these climate impacts start really affecting us, then the impact on our economies really gets worse. So we're losing prosperity on the one side, we're losing the resources we need to actually then deal with the problems. And the longer we leave it, the more expensive it's going to be to deal with those problems, to make those changes that are needed. So we need to get a grasp on this situation soon. We can't just leave it to our kids to deal with this. It's just not fair. And as I said, worrying about the animals is one thing, but worrying about our economy is another good reason to be concerned about this. So these are some events you can see, the Fort McMurray fire being a good example, the most recent sort of very significant climate-related event that's hit Canada. And these are insured losses. So something in the order of $5 billion of insured losses were incurred as a result of the Fort McMurray fire. But that's just insured losses. The actual cost to the economy is estimated to be something in the order of 3 to 4 times that. When you think about all of the evacuation costs and the businesses going under, and right? There's a bunch of impacts that aren't measured in insured losses that make that number much bigger. Perhaps more importantly, people are dying as a result of climate impacts. Look at the fires that are happening at the moment in western US. This is serious. We need to do something about it. So that's the big picture stuff. That's kind of the Chris Howarth hat, if I can put it like that. Now I'll be putting more of the Veolia hat on, my employer, talking about what this means for our industry, trying to make it a bit more specific to the water industry. So what does this mean for us? Well, this is a photograph taken near Saguenay in Quebec, the dam overtopped, and you can see pretty serious event. You can kind of see that we're in the house here. We are the house, perhaps. We are at the front line of this. Our water industry is exposed to these climate impacts more than most industries, perhaps more than any other industry. On the one end, we're trying to deal with stormwater management. We're trying to keep people getting good quality drinking water, trying to deal with sewage. So this is this is very much, these climate events affect us, very acutely. And at the same time, it's our job to keep providing those essential services. You look at COVID-19, people were maybe willing to put up with a little bit of impacts from some industries. If you can't, I don't know, go watch a hockey match, it's not great, but maybe it's not as bad as not being able to drink the water that's coming out of your tap, right? So our industry is an essential service. That's why we were named as such by the powers that be, and we have to hold that line. It's our job to give people the water they can drink and deal with their sewage. And if we don't do that, then you don't want to think about it, right? So absolutely critical that we hold the line, but it's not getting any easier. This is a little bit out of date now, but showing intense hydrological events, as they call them, storms, flooding, those kind of things. And again, trend's pretty clear, right? So what does this mean specifically? What about the specific impacts to our industry? So there's kind of two ends to it, I suppose. More intense rainfall, more intense storm events causing flooding, and longer periods of without rainfall, of drought, and that leading to things like wildfires. So those are really the sort of big picture things, and those are the things I'm going to be drilling into a little bit more in terms of what we can do about these things, because these are the things we're facing. As I said before, a lot of this comes down to resources, about our ability to react. We have to mitigate, we have to reduce our impacts on the planet, but we also have to adapt to the impacts that are clearly already happening. So adaptation takes resources. We have to invest in our infrastructure and various other things as well, our management systems and all the rest of it, to get ahead of this, to be able to deal with those impacts. And that takes resources. Another sort of aspect of resources here is that water is the single biggest consumed resource by humans. We use more water than we use anything else. It's for agriculture, for industry, mining, and domestic use, of course. So as well as needing resources to adapt, we also have a control over the biggest resource, and it takes a lot of resources to do that control. Think of energy and wastewater treatment, for example, or distribution systems. So we're in a position to manage things more efficiently, to mitigate our impact, and also to do things like resource recovery. Look at wastewater reuse, for example. So it's all sort of hinges around resources. Okay, making it more specific now. So I'm involved in treatment. One of the main things Veolia does is provide treatment technology. We're a manufacturer. So now getting into some of those things. What can we do about treatment to respond to these situations? How do we adapt our treatment? Starting with wildfire. So this photograph was taken in Fort McMurray, the 2016 fire. I think it's fair to call that like a biblical proportion of fire, right? I mean, how the people got through that, who were facing this thing, is beyond me. Brave people, because that's scary. Just looking at that photograph scares me. So yeah, incredible really how people were able to deal with that. What this meant for their drinking water. So firstly, you've got a short-term effect. The people evacuated, so there weren't that many people drinking the water. There were some, of course, the emergency services, but they also needed water to fight the fire. The fire was obviously getting into the city. They were trying to protect buildings. They were using the hydrants to do that. So make as much water as you can in your water plant and get that out into the distribution system to enable those firefighters to do their work. So that was part of the water demand sort of thing. Also, if you lose a building, then the supply line feeding water to that building can fail. And they saw quite a lot of that in Fort Mac. And then you've got an open end on that supply line. So then it's hard to keep pressure in the system. You're trying to make as much water as you can to feed the hydrants. You're also trying to stop contamination getting back if you lose pressure, because you don't want to have to decontaminate your entire distribution system before people can come back in and re-inhabit the city. So keeping water pressure, make as much water as you can. That was their immediate challenge. In the medium and longer term, you've got water quality issues. So the catchment area, the watershed has burned in large areas. So that does a few things. Firstly, you lose that kind of sponge effect that the forest gives you, that slows water down, that gives you a sort of buffering effect, and also gives you a cleansing effect. So you've now lost that canopy, you've just got ash on the floor, so when it rains, you get very rapid runoff of really ashy, sediment-laden water. So a lot of variability, a lot of water quality issues. You also get changes in the nature of the water quality, sort of chemistry. Organic carbon changes, things like phosphorus get released. That can lead to algae problems and the particulates from the ash. So you get these sort of medium and longer term effects, and they can go on for years or even decades. On a fire of the scale of Fort McMurray, you could expect that to probably still be causing problems, 10 years from now even. So big problems. In some ways, Fort McMurray was fortunate, believe it or not, because they'd done a big drinking water plant upgrade in 2014, increased capacity, improved technologies. Part of that upgrade involved one of our processes, the ActiveFlow process. It's a clarifier. I'm going to be talking a bit about ActiveFlow. It's a kind of common theme here, so I'll give you a heads up on that now. That is it's a robust process, and that helped them to make all that water. They were actually running the plant at 150% of design capacity at some points, and I guess ActiveFlow helped them to do that. It also is it's a chemical process, but it's a rapidly adjustable process. It's got a very short retention time, so it responds quickly, and that can help if you're trying to dial in chemistry and stuff like that. So I think it's fair to say that ActiveFlow was part of the solution to the problem, by far not the only part of it. Partly as a result of the Fort Mac fire, but also more broadly, there's a research study going on. It's being led by a lady called Monica Amelko in the University of Waterloo in Ontario, but it's a big collaboration. It involves, these are just a few of the names here that you see on the logos there on the left. City of Calgary was involved, Fort McMurray was involved, there's BC municipalities who've been involved as well. The fires we had back in 2018 burned some forest, and some of the ash from those burned forests were provided to the researchers as part of this research project. It's got various objectives, but one of them, as it relates to the treatment side, is to try and look at what those constituents do in terms of treatment. So taking ashes and doing treatability tests, you could say. For example, what is the optimum chemistry? What types of coagulants or polymers or even activated carbon are you going to need to be able to treat that kind of material, those kind of ashes, if they're running into your raw water? And it helping people get ahead. So if you've got a sense of, well, it's this type of anionic polymer or whatever, then maybe you can order some of that if you see a fire coming, and then hopefully you're going to stay ahead of this thing. So just a little bit on ActiveFlow and how it works. Conventional clarification is a pretty common thing. It's been around for a long time. Coagulant and polymer addition. So firstly, you add coagulant. That destabilizes your particles. So when particles are in water, they're just happily floating around. You add in coagulant, it destabilizes them. They start to come together, but only in very fine flocks, very small flocks. So then you add a polymer. Both of those things are charged. The coagulant and the polymer are charged. So what that does is like a magnet. It sticks everything together, kind of glues it all up. The polymer in particular glues it all together and makes a flock, a nice tightly bound group of particles. And if you've got a flock, it's easy to remove. You can clarify, you can settle a flock more easily, you can filter a flock more easily. So conventional clarification, like I say, it's been around a long time. ActiveFlow kind of brings a twist on that by adding very fine particles of sand, and we add that along with a polymer, and what that does for the chemistry is it gives you a nucleus. It helps the flock to form, especially if you've got a lot of sort of very light, fluffy material, organics, maybe even dissolved organics, for example, then you can start to get them coming together, but having a piece of sand to build that flock around can really help. So it can help the chemistry, make it a bit more efficient, a bit better performing the chemistry. So that's what a flock looks like when you've added sand to it. You can see the sand particles in there quite clearly, and then the fluffier organic material. What that does, as well as providing a nucleus to help build the flock, it also provides density. Sand is dense. So you can imagine how fast that thing settles relative to if the sand wasn't there. It's a very big difference. It settles like a rock, pardon the pun. That gives you much more rapid settling and therefore a more compact process. And that's what I was mentioning a minute ago about short retention times. It's because it settles so quickly when you've put sand in the flock. by having that rapid settling, you have a small process. So these are just to give you a sense of how it compares to some of the other technologies. High rate clarification, you know, DAFs can go pretty fast as well, but ActiveFlow, I think, is the fastest clarifier, certainly the fastest clarifier I'm aware of. So very compact. Compactness is good because it also means it's generally cheaper, less capital cost, less civil works, you know, smaller basins and those kind of things. So this is how it looks like in the diagram. Coagulant coming in from the left, you see the raw water. Then mix that up, give the coagulant sort of full mixing, so it's fully mixed into the water. Then going into the next stage, the flocculation area. This we call the turbo mix process. So what's happening in here is the polymer and the sand are being introduced into a draft tube. So that thing you see in the middle is a draft tube, and that's got a downflow mixer in it, drawing the water down through that draft tube. In there you've got high energy mixing. That gives the polymer and the microsand a good stirring up, so that mixes it all into that water. And then it comes out of the bottom into a much more gently mixed area, and that allows the flocks to form. They need to be gently mixed to sort of slowly come together and build up into a bigger and bigger flock. The water then goes to the next zone, which is the settling zone. Sludge settling to the bottom with a scraper to move it into the center. The water goes up through lamellar plate settlers, helps to catch all of the particulates, and then overwears over the top and out. The interesting bit is the sludge line. So if you see off the bottom of the settling zone there, you've got the sludge withdrawal and a pump, and then it pumps it around. So if you follow the orange line around, that goes to a hydrocyclone. The hydrocyclone separates the sand from the organics. You get very high shearing in the hydrocyclone. It's a vortex, so it spins very fast. The sand, the denser particles go out of the bottom, about 10% of the flow. The remaining 90% or so of the flow goes out of the top, and that's the organics, that's the sludge. So you're not constantly adding sand, you recirculate sand in the system. And that leads to the third benefit of adding sand. So I mentioned about the nucleus to improve the chemistry. I mentioned about the settling rate, the density. The third reason you do this is the sand going around gives you resiliency. You've got sand in a loop. We're running sand at concentrations of something like 4,000 milligrams a litre, you know, equating to TSS. So loads of sand going around and around. So if your influent TSS varies by 100 milligrams a litre, that doesn't really upset the process because the process is running at 4,000 milligrams a litre in that circuit. So it's a more stable process, more resilient. Okay. Enough about ActiveFlow for now. Now, another issue from climate change is algae. We're seeing more and more concern around algae, and it's for a few reasons, but a lot of them related to climate change. Temperature would be one. Algae likes warm water to grow. It's around now, September, you know, August, September is commonly the sort of time of year when you're going to see algae growth happening. Algae blooms, these things kind of go nuts. Another thing you need to grow algae is nutrients, and so when you have intense summer storms, that can wash nutrients off agricultural land, fertilizer, and put that into the receiving water, into the creeks and so forth, into the lakes, and giving the algae the nutrients they need to grow, to bloom. And sort of related to that, you can have flow issues the other way, as mostly over summer the flows slow down, so you have less dilution. And that also gives algae the conditions it likes. It likes it to be pretty still with enough nutrients and enough temperature. So a lot of these climate events, these climate changes are giving algae those conditions. Just think I should probably move that a bit. Another thing to say, so what is algae? Algae is a generic category of a bunch of different organisms. They all, you know, there's a lot of different types of algae. That's what I'm trying to say. Some of them cause some issues, some of them cause other issues. If you've got an algae bloom, then they're all going to create a TSS issue, just the mass of material, the cells, the algae cells. So that can overwhelm clarifiers, block, you know, plug filters, those kind of things. So TSS is common to all types of algae. Some types of algae produce, you know, release dissolved contaminants that give taste and odor issues. So that can be another problem. And perhaps the biggest concern is toxins. So there are some types of algae, particularly cyanobacteria, blue-green algae, that release cyanotoxins and particularly microcystins. So those things are damaging to the nervous system. There's been some reports in the media of dogs, swimming in lakes and then dying, and they think that certainly it could be related to those microcystins. They are very bad for nervous systems on mammals. The Canadian Drinking Water Guidelines were updated in 2018, and they have a guideline for microcystins now. 0.15 micrograms a liter, I believe, is the number. So, it's a thing. The regulators are aware of this, and it's something we need to be aware of as well. So, okay, if you've got an algae issue, what do you do? Well, firstly, you should try and avoid the algae issue in the first place. So, I don't know, try and keep the dilution going, try and avoid the nutrients getting into the receiving water, into your raw water source. That's not always necessarily very practical. So, if you do get a growth, then what do you do? Treatment, of course. Really, with algae, you firstly want to get the cells out, all of that TSS, all of that mass of material, and you want to do that as gently as possible. You can imagine those cells a little bit like balloons full of nasty stuff. So don't pop the balloon. Try and gently remove the balloon, some kind of clarification typically. Then if you after you've got those out, then some of those balloons will have already popped anyway, and so you might have a dissolved issue to deal with also, and that's where things like oxidation can come in. Chemical and biological treatments can be effective to remove those dissolved materials, those microcystins, for example, which are dissolved. So a multi-barrier approach is probably what you want to be thinking about. Careful operations, a bit of a vague term. I guess maybe the starting point is just plan for this. If you have a raw water that could have an algae bloom in it, then it's a good idea to plan for what you would do if you had an algae bloom in your raw water. If it could happen, it might happen, and it's more likely to happen with climate change. So plan for it. What are the tools you have available to you? What can you do to try and prevent the growth in the first place? What treatment tools have you got in your plant to be able to respond to that? Do you have a clarifier? Maybe as you're looking at your upgrade, should you be thinking about putting in a clarifier if you don't already have one? And be careful. Don't pop those balloons. So, for example, sludge. There's some research that shows that if you have a lot of these algae blooms all together, you leave them in a tank for a bit, then they start lysing and popping all those balloons. So don't recycle water from your sludge treatment, your residuals management system, back into the plant. Keep that, when you've got it out, keep it out. Something else you can do is add on something to the ActiveFlow. I said I'd come back to ActiveFlow. I apologize now. You can add carbon in the ActiveFlow process, powdered activated carbon. So if you have got those dissolved issues, those dissolved contaminants, then carbon can be a way to absorb them. And one way to use carbon is with the ActiveFlow. It's a lot like the microsand. We recirculate carbon in the system as well. We add a tank up front, gives it some contact time, gives it some mixing, and then we recirculate carbon around the system. So we run very high carbon concentrations, and that also gives you very efficient treatment. You're not just putting the carbon in and having it go out the other end. You're recirculating it so you can run high concentrations of carbon and be very efficient with the carbon. DAF is another good technology. Veolia offers DAFs as well, high-rate DAFs. Broadly speaking, DAFs and ActiveFlow remove a similar amount of algae, the numbers here. There's some algae that are better for DAF, maybe conversely with ActiveFlow. I'm not a great expert on this stuff, but safe to say that both do a pretty good job of removing algae. So clarification will give you that first step to get rid of the mass of algae. Drought hasn't been too bad this year, not in BC. This is a good website, incidentally. If you're interested in drought, then there's the link on the bottom there. It gives a sense of what sort of issues we're facing. You can see in the Okanagan, it's been pretty dry. This was at the end of August. The wildfire in Penticton was certainly a concern there for a while. So quite a useful thing to keep a track of what's going on in terms of drought. I'm going to be talking about disc filters tomorrow, so if you're interested in tertiary filtration, disc filters, then I'm not going to say too much about it now because I am presenting on that subject tomorrow. And in fact, I will stop there in the interest of time and keep going. So storms. We've talked about sort of dry conditions. Now, what about wet conditions? Storms can affect raw water sources in quite a big way. So you can see the hydrograph there. That was a storm in 2013. That's the Rockies. You can see Calgary in the middle of the graphic there. What happened? It was in late June. Still plenty of snow in the Alpine. A very intense storm came over, and instead of just passing through, it just sat right on the Rockies and just dumped. So washed all that snow off, and just the rain coming out of the sky as well. Huge, huge flows. And you can see in the middle photograph there, that's the Glenmore Dam, top middle, and that's water from the dam goes to the Glenmore water treatment plant in Calgary, serves a good part of Calgary. They were trying to treat some pretty challenging water, high turbidity. It's not unique to Alberta. We've seen events like this in BC as well. So the photograph in the middle there is the Seymour Reservoir in Metro Vancouver. The photograph on the right is the Comox Lake on Vancouver Island. It's one of the tributaries coming into the lake, bringing in an awful lot of turbidity with it. So yeah, these things are happening. It's really to do with intensity. If you have an intense storm event, especially if you have a disturbed watershed, your catchment area has been logged, for example, then you can have these kind of issues. It's happening in quite a lot of BC. So this is some data from the Glenmore water plant. There's quite a lot in here. The axis on the right is raw water turbidity, and you can see the numbers there going up to 4,500 NTU, which is soup, right? That's mud you're trying to treat at that point. Those are the red lines. So if you look at the spikes, those are storm events that have released turbidity in the raw water. That's what's coming into the plant. And you can see going back, since 2000, they were seeing fairly frequent storms, normally summer events, with a few spikes. So if you look at 2005 there, for example, a reasonable spike. The green dots are the water going to the filters. So after the clarifiers, on top of the filters, what are they trying to filter? You can see, again, looking at that 2005 event, they were seeing clarified water turbidity in the order of 30 NTU. That's a high turbidity. You don't really want to be trying to filter 30 NTU. That's going to overwhelm the filters. It's certainly going to mean short filter runtimes. And even the next year, more like 45 NTU. Not great to put on the filters. Then that 2013 event happened that we just saw the photographs from the Glenmore there. Off the chart, right, or nearly off the chart. 4250 was the NTU they saw in their raw water at that. You can see the red line there on the right-hand side. Just crazy. Never seen anything like it before. But fortunately, back around 2010, they'd installed the ActiveFlow process, and that kept their clarified water down around less than 5 NTU. So there's a good guy there, Kelsey Kundert. He's kind of guides the operators. He's like the process expert that helps the operators in the team. He was saying that really they wouldn't have been able to do this if they hadn't have had ActiveFlow. Changing gears a little bit now, so still storms. What about the wastewater system? If you have a storm event in your collection system, you might overwhelm your collection system. Pipes are only so big. Pump stations can only handle so much. So you can have an overflow event in the collection system. That is particularly an issue where you have combined sewers, where they are designed to receive storm water, but it can be an issue in sanitary systems as well, inflow and infiltration. You also can only design your wastewater plant to handle so much water. You can't design it for peak hour, 100-year storm event sort of a thing. So there is a limit to how big you can build it. So normally, wastewater plants are designed to only treat up to a number, and then anything beyond that needs to be bypassed at some part of the process. In 2015, Canada apparently had 205 billion litres of untreated sewage discharged into the environment. And that's a lot. That's a big pollution load. So it's becoming a bigger issue. Regulators are looking at this, people thinking about this, doing something about it, regulating it. So it's an issue. That's a lot of load. It can be as much or more load than happens all of the rest of the year. Just those few storm events where you overwhelm the system can put more pollution into the environment than you do in your treated effluent for the whole of the rest of the year combined. So what do you do about that? Dealing with combined sewers, is probably a good idea. Separating sewers, Metro Van's doing a lot of that. But it costs a lot of money, takes a long time, and is disruptive. You're digging up roads and so on. So there's probably a balance to be struck between dealing, getting the best possible collection system, which doesn't leak at all, perfection, right? And treatment. If you're going to do treatment, you need to screen. We need a glass of water. Thank you. You need to screen first. That's because you need to protect the downstream clarifier. Excuse me. Then you can clarify to get out the contaminants, and then disinfect if you're going to a bathing water, for example. Okay. ActiveFlow, excuse me. ActiveFlow is a clarifier you can use for this application. You can see the orange line there. It's got a very short retention time, so something in the order of 10 minutes to go from startup to 80–90% performance. You can put ActiveFlow in the collection system at things like pumping stations where you would have your overflow events, or you can put it at the wastewater plant. We've done both. If you put it at the wastewater plant, you've kind of got a benefit that you can use it for different things as well. So the graphic on the left there shows a wet weather event. You would normally put this downstream of the headworks, so design your screening and your grit removal to do that peak flow. But then your primaries, secondaries, all of that can be a lower flow, monthly average or whatever you want to design for, max month, and send the rest of the water when you have those peak flow events through the ActiveFlow. But then that means it's not going to be used that much, right? You're not going to have that many storm events in a year that are going to cause that bypass to happen. So for the rest of the time, you can put it at the back of the plant as a tertiary treatment. It does a great job of removing TSS and phosphorus. So maybe if you're doing tertiary filtration, for example, you can put it before the filters, and that'll take the load off the filters. It'll also mean you've got cleaner water if you're doing UV disinfection, for example. So use that same installation, that same piece of equipment to do wet weather and tertiary. Something else you can do if you're at the wastewater plant is something we call Bioactive Flow. It's like a twist on it. So maybe just actually, before I go there, this is a conventional activated sludge system. So for those who are familiar with this kind of technology, this shouldn't be too unusual. What we do in this case is we've got the ActiveFlow, but before the ActiveFlow, we put a high-rate biological contact tank, solids contact tank. So you still do the bypass. You take some of the water after the headworks, anything you don't want to send through the mainstream. And you also return some of the activated sludge out of your secondary clarifiers into that high-rate contact tank. It's about 15 minutes retention time. That gives you biological activity that absorbs soluble BOD. That's the first thing that the biomass is going to go for. It sucks in all the soluble BOD. Then that goes into ActiveFlow where that biomass is clarified, and the sludge out of ActiveFlow goes back to the aeration system. So this is about removing soluble BOD and keeping sludge in the system to avoid losing any of that valuable biomass that you've taken so long to build up, right? That's one of the biggest challenges with storm events is they can wash out biomass. So that's the other reason for doing this, soluble BOD and keeping your biomass. So here are some numbers. If you just do the ActiveFlow thing without that biological bit, then you can do a great job of TSS. It's a clarifier. It's good at removing TSS. But the BODs may be a little higher. Depends how much soluble you've got. If you do the Bioactive Flow, then you can see the BODs come right down, and you even do a bit of a better job on the other numbers as well. So you can reliably meet secondary treatment goals, 25 ton of levels easily with Bioactive Flow. It's being installed in the new North Shore wastewater plant, the replacement for the Lionsgate wastewater plant. Metro Van's putting this in. 2 ActiveFlows, 60 megalitres a day each capacity. So, it's happening in Canada. And I'm pretty tight on time now. I just wanted to leave a bit of time for questions. But this photograph, you're probably thinking, why is he putting that up? I love this photograph. It's from northern India. They have a lot of rainfall there. It's in the foothills of the Himalayas, maybe a bit like the North Shore where I live. Plenty of rain. So lots of creeks. And what they have there is trees that grow roots that sort of dangle down. So what the locals have done is take those roots and weave them into things like bridges. And so I love this photograph because it shows that you can build a really useful piece of infrastructure with zero footprint, right? What's more sustainable than that bridge? And it's getting kids to school so that maybe they can learn how to build more bridges or whatever, or save the planet. I don't know, but I just love what that shows. And if all of our engineering could be that sort of sustainable, sort of going back to where I started, I suppose, really, then wouldn't that be great? And in some ways, wastewater plants are. We use biology in our wastewater plants to treat sewage. So, there are things we are doing that are great. So let's do more of that. So I'm not sure if we've got any questions, but maybe I should thank you very much for your attention so far. And if there's questions, then happy to answer those.
Thank you very much for that presentation, Chris. That was great.
Thank you.
Right now on the board, we don't have any questions. I want to thank you for your presentation today on behalf of the EOCP, and thank you for coming in.
Thank you very much for having me. I appreciate the opportunity.
And for everybody watching, we will resume on the water sessions here at 4 o'clock for our very last session of today. Thank you very much.